All right, and we're back. Hopefully this is the last video for section 1-2. So again, we're in this whole mathematical models chapter, but remember we're talking about all different types of functions. Just a couple more functions to talk through today. We talked about polynomial, we talked about power. One thing I wanted to make note of in power, please don't think of them as any sort of different type of function. They kind of like fit in specific places, underneath the umbrella of polynomial functions, you have this case of power functions, where it's just y equals x squared, y equals x to the third, and so on, where it's just that first term. This I would consider its own type of thing. It's root functions, where it could be square roots, cube roots, whatever it may be. Just know that those functions could also be represented as fractional exponents. And then here, reciprocal functions, I would consider those like more rational type functions, where you have 1 over x. But again, rational functions are its own thing as well. I guess I lost those, wherever those are. Algebraic ones, yeah, blah, blah, blah. Oh yeah, here, rational functions. Those are their own thing, their own separate entity anyway. And again, those are the weird ones. And then I think I got through all of trigonometric. I did this example, correct? Perfect. Okay, so we're in trigonometric, right? We're still, we talked about sine, we talked about cosine, we haven't touched tangent yet, so let's talk about tangent. Think. Do I have to play? Oh, it's stuff. Is it stalled out? Pause. Play. No. Stop. Play. There we go. That did the trick. The tangent function is related to the sine and cosine functions because we know tangent x is equal to sine over cosine. Tangent is equal to sine over cosine. That's one thing that we got to stick in our brains. Tangent is equal to sine over cosine. Tangent is equal to y over x. The y coordinate divided by the x coordinate. And its graph is shown down below. We'll talk about that in a second. It is undefined. You know, think about it this way. When is tangent undefined? Well, it's kind of like a rational thing, right? Because it's a fraction. So you got to think about it as, well, when cosine of x is equivalent to 0, then tangent is undefined. Well, when does cosine x equal to 0? So think about it on the unit circle. When is the x, what angles where the x value equal to 0? It's the 90 and the 270, right? The pi over 2 and the 3 pi over 2. So that means x cannot be equal to, well, it is undefined when x is equal to pi over 2 or 3 pi over 2 and all rotations. Yeah?
I have a question. Would it be useful for us to rememorize the unit circle?
It'd be a great idea.
Okay.
Yeah. Or have one at least printed out for yourself that you could kind of like reference if you need to. I got to be honest, we'll use it enough that you'll remember. Its range is negative infinity to positive infinity, so it's actually different from sine or cosine in that now the range. Excuse me, voice crack. The range is now all real numbers, where the domain was is now restricted. Because it is going to go forever up and down, but it's not going to go forever left and right. There are gaps and breaks. There are discontinuities in there. Notice that the tangent function has a period of pi. Has a period of pi. That means every pi it's going to start back over again. So that means instead of rotations of 2 pi, it's actually rotations of pi that will start back over on itself for all values of x. And here's the graph. Okay, here's the graph of tangent. We see the vertical asymptotes, and remember that's kind of what we talked about yesterday with rational functions. Wherever you see where the denominator is equivalent to 0, that's either a hole in the graph or a vertical asymptote. Here we see the vertical asymptotes at wherever cosine x equals 0, pi over 2, 3 pi over 2, and it could keep going forever left and right, negative pi over 2, negative 3 pi over 2, and so on. We have those vertical asymptotes going up on the right and down on the left for each one of these periods. Okay? And it's running through the axis at pi, right? It's running through the axis at pi. It's equaling 0 at pi. Why is that the case? We'll think about for the fraction equaling 0, I would need to set the numerator equal to 0. Well, where does the numerator equal 0? Where does sine equal 0? At pi. Think about at pi that sine is equaling 0, the y value is equaling 0 in the unit circle. The remaining 3 trigonometric functions, cosecant, secant, and cotangent, are all reciprocals of sine, cosine, and tangent functions. Their graphs are shown, they say in Appendix D, but they're later on in the book. Okay, two more types of functions to talk about, exponential and logarithmic. We will spend an entire chapter going over the exponent rules, and then, not entire chapter, excuse me, entire section later on in chapter 1, and then an entire section discussing the logarithmic rules as well. That'll be sections 1.4 and 1.5. The exponential functions are the functions of the form y equals b to the x. F of x is equal to b to the x, where b is the base, and that's a positive constant. That's important to remember. Our base must be a positive constant for it to be an exponential. It could be fraction, but it can't be negative. And it can't be 0 either, because 0 would turn it into just a flat line. The graphs of 2 to the x and 0.5 to the x are shown. In both cases, the domain is all real numbers, but the range is restricted. I could plug in anything left or right, but the range is going to be different. The range is just above the x-axis for both of those. That is true for everything except if I add or subtract it on the end, then it's going to shift it. It's a vertical shift up or down. So in that case, it would change the range depending upon where that asymptote may fall. And there is an asymptote here, right? For any exponential function, it's going to get closer and closer and closer to the x-axis without ever reaching it. So there's an asymptote here. So if I shift it up or down, that asymptote will shift with it. If I add or subtract on the outside, the asymptote will shift with it. Notice that the difference between 2 to the x and 0.5 to the x is one is increasing where the other one is decreasing. So 0.5 to the x, any number between 0 and 1, that will make it decrease. That's an exponential decay rather than an exponential growth. Exponential functions will be studied in section 1.4. We'll see their uses in population growth, radioactive decay, all that fun stuff. Okay. And then our last type is the inverse of exponential. Okay, we had exponential functions, and then now we will have logarithmic functions. Still see some pencils moving. I'll come back to the slide if we need to. Logarithmic functions. The logarithmic function, most basic one, is f of x equal to log base b of x. Log base b of x, where b, again, is a positive constant. Just like the exponential function, the base had to be a positive constant. Same thing. The base of the log must be a positive constant for these rules to exist. It's the inverses of exponential functions. Again, we're going to talk about them at great length in section 1.5 and all of the properties, like if you add and you multiply on the inside, if you subtract and divide on the inside, all those sorts of things we're going to talk about in section 1.5. This shows the graph down below, shows the graphs of 4 logarithm functions with various bases. It's really interesting to see what happens if you change the base. Okay, take a look and see what happens as you change the base. So here, this most vertically stretched out one is log base 2 of x. As I increase the base of the log, it gets shallower and shallower and gets closer to the x-axis. So in relation from log base 2 to the log base 2 of x or log base 10 of x, log base 2 of x is a lot more vertically stretched out than log base 10 of x. And again, we will use a lot log base e of x, or the natural log of x. But again, we're going to talk about that a little bit more in section 1.5. The domain here is what is restricted because, think about it we'll talk about inverses a little bit later on in this chapter too, but the domain of the regular function is actually the range of the inverse, and the range of the regular function is actually the domain of the inverse. So if I think about going back to exponentials, where I had the domain was all real numbers, but the range was restricted. Now the opposite of that, the domain is restricted, but the range is going to be all real numbers. It will continue to go up and down forever and ever, but I'm only going to stay to the right of my y-axis, 0 to infinity. Again, that being said, that is if I do not shift it left or right. If there's adding or subtracting on the inside of the logarithm, then that means that it's shifted left or right. Okay, that's going to shift my domain, and it's also going to shift my asymptote. So remember that the asymptote for an exponential was a horizontal line. The asymptote for a logarithmic is my vertical line, right? There's my asymptote, kind And if I shift left or right, that's also not only going to shift the domain, but also shift that asymptote too. So if I shift the logarithm 3 units to the right, say an x minus 3 inside the parentheses, that's also going to shift my asymptote. So my asymptote would be at x equals 3 over to the right. All right, so last example here. Classify the following functions as one of the types of functions that we have discussed. Okay, so what do you think about A? That's an exponential. B to the x. Number to the x power. That is an exponential. It's important to identify the look of the equation because that's going to tell you certain rules to follow. Okay? Because all polynomials will follow certain rules. All exponentials will follow certain rules. All rational functions will follow certain rules. I could really talk about B in two different ways. I could either call it the power function. It's just a power, but remember that power functions are also polynomial when it's of this form, when it's just the x to the certain power form, when it's the x to the positive whole number power, x to the fifth, x to the third, x to the fourth, whatever it may be. This one, what do we think about this one? Algebraic, yeah, because I see a couple of different things going on. Algebraic. I see, it looks rational, yeah, but there's also a root within it. So that means it's it's algebraic. It's got two things going on. It's a combination of the two. And what would I consider D? What would I consider D? What do you guys think? Polynomial, yeah. Polynomial. If I wanted to be really specific, I would say a quartic. But it is a polynomial. Good. All right, I knew it was going to be a short notes day today. That's perfect. That's great. All done. Spend the rest of the time working on your assignment, please.